Pleased to be back. Thank you for inviting me and giving me a chance to tell you about some of my work in sports analytics and why I think it's a great topic for AI. I think I was here in 2016 and kind of presented some of my early results. It's like an update. Feels like coming home. I thought I'd start very high level, just a bit of an idea of what's going on in sports analytics. So it's a growing industry. Got 2021 study, and we especially on the data provider side. So we have three here. I mentioned three big companies. When we go there, so Randy mentioned Sportlogique, which is based in Canada and focuses on hockey. And this is what the website looks like. And I worked for them for 2 years, so full disclosure. Stats Perform is kind of like a competitor for Sportlogique, focused more on soccer. Sport Radar is the big fish in this pond. They had a huge IPO. The CEO of Sport Radar came and rang the bell of the New York Stock Exchange. It was a big deal. And they feed more the betting market, bookmakers, syndicates, where Sportlogique and Stats Perform and them were teams as clients. Okay, so we see a lot of growth in industry, also increasingly in academia. The most visible conference is the MIT Sloan Conference, organized by the business school. And it's kind of a trade show for sports analytics, but they do have research papers. And I'm seeing more and more papers in AI-related conferences. Michael Bowling wrote a very nice paper on curling. There's journals on the sports statistics side. I want to mention that we've been running a sports analytics group at SFU for I think about 6 years now, and U of T has started one. Timothy Chan, who's a CRC, got quite a big grant to start sports analytics at U of T. So within Canada, we have two groups. You can get a degree. DeepMind has made a fairly recent blog post on AI and sports and different ways in which AI can help. Maybe I won't click on that now, but I can recommend it if you just want to get a quick taste. So why do I think it's a great topic for AI? Many AI topics are relevant. Maybe all AI topics are relevant, including sequential decision-making, multi-agent systems, right? We've got players, we've got teams. Spatial temporal event modeling. So we have complex data about what player did what, when, and where. I will show examples later. It's really all about interactions among players on a team, teams interacting with each other. So you can do network analysis, relational learning. One of my favorite topics that I hope to have time to address in some detail is representation learning. So learning to model individual players. So I love it. So let me talk a bit about the content. So at a high level, I think you can make out three main areas. So one is tracking, data collection, right? Figuring out which player is doing what when. And if you do this from broadcast video, what Sportlogique does, then it's a really interesting computer vision problem. Then there's prediction, which is kind of the obvious task. Then we need to figure out who's going to win the match. But you can also do prediction for things like who's going to score the next goal, who's going to get more red cards. And the third major area is player evaluation. Which player is doing well where, who should we draft, who should we trade. You guys heard of the movie Moneyball? Can I see show hands? Okay, so Moneyball is in this area. Okay, so I'll be focusing on player evaluation and just kind of an overview of the topics that I'd like to talk about and how they fit together. So at first, I'd like to introduce this concept of expected value, success probabilities. And I think that's the fundamental problem of sports analytics. If we can estimate success probabilities, we can do everything else. It's a big idea that I'd like to get across today. And in particular, if we have success probabilities, we can assign values to actions, and then we can assess players according to the values that they perform. Right? If we want to understand the performance of individual players, we can add player representation learning. And then there are different ways to learn success probabilities, but the one that I've been working on with my group and that I favor is using deep RF. So this is an application of deep reinforcement learning. Okay, so now I'm going to fill in the details of this picture. Let's talk about the expected value function. I'm giving reference to a couple of my papers that are sort of, I think, pretty good as introductions. So I'll state the problem abstractly, and then I'll give a little demo. The input is a match history. So at any given time, you've been watching the match, and you want to ask, what is the chance that my team will succeed in the future? And so the key thing that makes it a bit different from, say, classification or even predicting the next item is you're looking ahead to future success. Okay. Again, I'll make that concrete. So success is vague, but that's an advantage because you can define it according to your application. So I'm giving some examples here of success concepts that people have used. So an obvious one is I succeed if I win the match. So then that gives you a concept called win probability in sports. You could ask, okay, someone's taking a shot. What's the chance that the shot actually is a goal? That's called expected goal or X goal. So in sports analytics, they always write these X goals. If you're looking at something like basketball, you could look at what's the expected number of points from a possession. The success notion that I tend to use is who's going to score the next goal, regardless of how long it takes. Okay, so that's the abstract. So let me see if I can visualize this concept. Let's first tell me what I'll tell you what you're looking at here. So this is the demo from Luke Bourne's group. So Luke was at Harvard, and then for a few happy years we overlapped at Simon Fraser, and now he's back in industry. He worked with Barcelona, so he did this nice demo. This is a match soccer, Barcelona against Real Madrid playing in white, Clásico, as they say in Spain. So on the left, you see video feed. On the right, you see two-dimensional representation. Player is moving, every player is labeled. That's called the tracking. You see the ball. Okay. We can run this. Okay, it's running. Okay, so here you see the game developing. And at the bottom, you have what Luke Bourne calls the value ticker. So the system is watching, and at every point, it's assessing what the chances are for Barcelona scoring. More exactly, the difference in chances, but that's so important. And let me maybe go back to the beginning so I can highlight more. Okay, so here, if you look at the real match, Barcelona is taking the ball away from Madrid, but they're under pressure. They might lose the ball, and now they manage a backward pass, which secures their possession, and so their chance of success goes up. Right, and then during the attack, they manage another backward pass, getting Messi to be free, and their chance of success goes up again. Okay, so the system is continuously watching, and at every point it's saying, is Barcelona going to score or not? Okay, here's a similar value ticker from my group. This is in hockey now, a game between the Pittsburgh Penguins and the Columbus Blue Jackets. And so we're plotting in orange the chance that the Penguins score, and here you can see the Penguins are attacking. The system is like, okay, they might score, but Blue Jackets defend, so it levels back out. And then around here, the Penguins are launching a dangerous attack and deflected, but they keep going. The system is getting excited, and they score. Yes, so you can see the excitement mounting. So I can see it. Okay. Okay, and then the game goes on. And I know not everybody knows the rules of hockey, so I'm just going to show you a short clip and explain how hockey works. But for now, I just want to pause and ask, so this idea that we're going to continuously assess success chances, like that's the main idea I want to get across. See those questions. Yeah, Russ.
Those should be calibrated.
Yeah.
Other times we say it's a 20% chance of scoring.
Yeah.
If you do that 100 times.
Yeah.
They score 20 times or not.
Well, that's what you want to see.
Yeah, is that?
Yeah, we have evidence. Yeah, we got studies on. It depends a bit on what method you use, and yeah. So generally, it's quite well calibrated. Luke Bourne has built a system for soccer. I mentioned that's extremely well calibrated. Like I almost don't believe it. So, yeah.
0.001, 0.002.
Yeah, it's like okay, I believe it, but we're getting.
So that raises another question that I found in working with the Oilers is the concern there is for being able to interpret the predictions, not for the requirements scientifically that there is a background to confirm your predictions are successful over historical period, right?
Yeah.
And that's one of the things that's different between how
Right.
academic scientists use, like Russ asked the question. But I can tell you that the
Yeah.
Oilers president and coach didn't care about that because they couldn't interpret it anyway.
Right.
What they did care about is whether or not the predictions were phrased in a way that was actionable, and that's what you've done.
Yeah. Okay, that's almost more for a question period. So yeah, explainability is key because you're talking to coaches, you're talking to players, and like there's like linear regression is way too complicated for them.
Yeah.
And I have kind of like we've written about 3 papers actually on how to interpret value functions learned by a deep RL system. I know it's kind of a different topic, but I'd be happy to show. I can at least explain kind of what our approach is. Okay, let me see if I can go into my little hockey demo. Here we are. Okay, here, ice hockey. So ice hockey is like soccer. Both teams have a goal. There's a puck, which you can sort of, I guess you can see it. And instead of using their feet to move the ball, hockey players use their sticks to move the puck. And okay. And then when they get the goal, the puck into the goal, then they score a goal. This is a historic moment, great moment in Canadian history. I hope everybody can remember where they were. Canada winning gold medal. For the international students, you know, it might be on the Canadian citizenship exam. So. I'm just kidding. And so soccer and hockey are actually fairly similar from an analytics point of view. So in sports analytics, they're called invasion games, where each side has its half and you're invading, penetrating, and they're continuous flow, right? Everybody is acting all the time. So continuous flow games are the hardest to analyze. Example of a quite different sport would be tennis. Each player stays nicely in their half and they take turns hitting the ball. Much easier. So I often joke, I wish I'd started with tennis. Okay, and so now since we started doing this work around 2014, 15, so this idea that you're going to assess players by assessing success probabilities really been pursued in a number of different sports by different groups. So I can say with confidence this really works for player assessment. And it's not just me. And we've also done work on soccer actually, I've been cited. But, so now what I like to say, so let's suppose we have these success probabilities, right? We have this value ticker. I'll get later back to how we learn it. So how can we use it to assign values to actions? And the idea is to look at what I call the impact of an action. So we say, okay, before the player acted, what was the chance of success? And after they act, what is the chance of success? And if the chance of success goes up, that's a positive impact. If it goes down, it's a negative impact. Okay, here's a quote from the Harvard Sports Analytics group that basically says, if you can do this, if you can compute this quantity, you can answer all the questions. Let's see. And Yeah, so here on the slide, I think I won't go into the details in the interest of time, but what traditional sports analytics did instead, they would define handcrafted metrics. So you may have heard of sabermetrics from baseball that have been used since the 1940s. And they have none of these nice properties that expected values have. But I think maybe within an AI group, I don't need to motivate expected utility so much. Okay, so we're going to do expected utility. I can come back to this. I mean, it is revolutionary compared to traditional sports analytics, but it's not for AI groups. So let's visualize the action impact. So I made some box plots. That's big enough. You can go back, okay. If we look at the averages here, they make sense. So this is for shots. Oh, wait. Okay, here's the mouse for shots. So shots tend to have the highest positive impact. That makes sense, right? That's how you get a goal. Another sanity check is if you have a face-off in the offensive zone that has a higher impact on your goal scoring chances than face-off in the neutral zone. And that makes sense because you're closer to the opponent's goal. Yeah.
I was wondering, before you remark the importance of making it continuous, that everything you showed look very discrete, like you have VAT max B plus 1 minus 1. And also I wanted to know, like, why making it continuous? Like, what is continuous here?
Okay, well, I'll answer that shortly. I'll come back to this, but well, we have the main thing is we have continuous space and time.
Yeah,
right.
Time should be continuous. Right?
Yeah, so now it depends on your data, and that's I'll come back to that. But I use what's called event data. Okay, I'll show you. But they're event data say, okay, this player made a pass, this player made a hit, and so they're discrete events.
Yeah, exactly.
So that's really what I'm referring to here. Yeah. Now that would be actually quite interesting if you had continuous. You started doing derivatives. That would be cool.
That's the reason behind my question, right? Like, if I make a pass to Messi, and like maybe I can model it with like some probability of being successful, like
right.
Goal which is Messi, but I don't need to model what everything is in between, right?
Okay, it's let me come back to that when I talk about the data. It's kind of a deep question, but
Well, practically speaking, no player is their coach is interested in a distribution of continuous approximate hits. You either hit the subsequent consequence or not, right?
right. So okay, so maybe I'll go into that just a bit more deeply. So Luke Bourne has this model, he calls it a 2-level model. And he says, well, at one level, there are the discrete actions where you say, okay, right, they did a hit, they did a pass. But at the other level, the players are moving. So if you think of something like hockey or soccer, they're basically trying to position themselves, for example, so that they're free. And so there it's really a continue, right? They're moving continuously, and you can talk about them improving their positions in their locations. So he calls that micro macro, something like that. Yeah, but I'm just looking at the events for now. Okay, one more thing I wanted. Well, okay, so I guess the other main point I wanted to take away from this is there really is a spread of action values, right? So it's not like a shot always has the same value. Takeaways have a big spread. So and that's because our model is always context dependent, right? So we don't just say, right, if there's a fixed constant value for a shot, it always is, where are you taking the shot from? How promising is it? And you see that in the spread in the box plot.
Green points and the red points.
Yeah, there's at the time there was an alternative method called SOAR. And so yeah, okay, I can go into that, but unless you really care about SOAR. So, okay. Okay, so now we can assign values to actions. Let's go to player rankings. And here we can take a straightforward approach. We just say, okay, for each player, we take all the actions and sum them up. And then that's their score in the season. And then we can rank them according to this. So we call this goal impact. Now I just have a couple sort of anecdotal evidence. I love looking at these rankings, and then I look up the players in the hockey news, you know, and see what the journalists say about them. And so, and on my website, actually, I tell some of these stories, but I'll just pick a couple here for you. So 2013-14, Jason Spezza came out on top. And one thing that's interesting about him is that his plus minus is atrocious, not a misprint. So plus minus is computed like this. If I'm on the ice and my team scores, I get +1. If I'm on the ice and my team is scored on, I get -1. So it's kind of mixing team performance and player performance. And that season he played for a very poor team, the Senators. Okay, I'm not saying the Senators are a poor team, they're often very good, but 2013 they were very bad. So, and then we have some anecdotal evidence that, you know, our analysis is correct in that for the next season, he asked for a transfer. So we're saying he's a lot better than his team, and him and his manager agreed. It's not usual to transfer. Yeah, I know it's anecdotal. The other thing this example shows is that we can actually disentangle the overall performance of the team and the performance of the player. Right? We're saying he's doing lots of actions that really should lead to goals if he were with an average team, but his teammates are not picking up. And that's kind of a long-standing challenge in sports analytics to tease apart, right? What the individual is doing versus how the team is performing. Here's another example, salary. I got Johnny Gaudreau, Mark Scheifele. And you can sort of see, you know, in the top 10 there, everybody else is making multiple millions except for those two. So according to our analysis, they're undervalued. Although, hey, I would like to have Mark Scheifele's salary even then, but okay. And again, we have anecdotal evidence. The next season, they went up to a $5 million contract. So again, the team, I guess it's the Jets, they agreed with us. Salary is interesting, as I mentioned, kind of one of the industry applications to figure out who to trade, how much to pay. Just something I want to mention that's interesting. So if you look at the same player and you say, oh, they're underestimated this season, and then you track what happens 2 seasons later, the amount of underestimation goes down. So basically, it's consistent with our model detecting early that this player is very good, but then their teams take like maybe 2 years, 3 years to catch up, which is great. I have to be careful though, NHL salaries are very complicated because they're highly regulated. So, you know, it's kind of a complicated story. Okay, I'll do this one quickly just because Randy mentioned explainability. So one way in which I try to make this explainable is because our ranking is an aggregate metric, right? We're summing. So if I say Erik Karlsson, for example, he was I think #1 that season, and I say overall he's great. Well, I can drill down. It's like a pivot table. I can say, well, what actions, where, in what context is he really good at? Okay, and then if you do that, you can find that, for example, he's really good at getting the puck on the left wing to help support an attack. Okay, so you can go very detailed with a coach, and then that's actionable. You can say, well, really, you should try to get him into these situations. Right?
Confounders?
Hmm?
What about confounders? What if he's really good because someone else on the ice is on the right side?
Yeah.
And it wasn't because the left side, it's because someone else was in that place.
Yeah.
That happened?
These are aggregate measures.
Still.
Does it have? Well, I haven't quite looked. It maybe happens less than you think. And okay, I can maybe come back to that. But part of it is we have so many data points. So in a season, we have 3.3 million events. So like these trends, these averages are really quite
Well, that's every time on the left, every single time, because the line also had this.
yeah, the lines, yeah. My favorite example used to be the Sedins with the Canucks. They were playing on the same line and they were identical twins. So now how are you going to tell those two guys apart, right? Are you going to say, oh, Hendrik is doing great? Maybe it's because he's playing with
In fact, the
Daniels.
same kind of drill down would distinguish them, like, because overall, they were different kinds of players, even though.
Yeah.
Yeah.
So I come back, okay, so that's a big jump. So for now, all I want to say is if I'm talking to a coach, right, and the coach says, okay, tell me more about where this guy is doing well, I can't answer that question. Then there's another question about how much credit he deserves for that, right? So, okay, so I hope to have shown you how you can use success probabilities to do player ranking. So I'd like to go a bit into how to learn them. And this is where I apply reinforcement learning. If there's one picture I'd like you to take away from the talk, it's this Venn diagram. So I think that sports analytics should be a major application area of reinforcement learning. Or another way, I think reinforcement learning has the resources for us to solve the problems of sports analytics.
Sorry, are you also saying that every sports analytics problems can be solved by
Close to it.
Or not solved.
Close to it, yeah. Maybe some. I also am working on drafting. Okay, anyway, as long as you have dynamic data, like over time, then yes. So that's my view. I like this big picture.
You just gave us an example that reveals the subtlety of why reinforcement learning in its standard description is insufficient, because in the question Russ asked, it was about actionable dependencies. And most of the work you work on is about trying to identify the dependencies to make actions.
Yeah.
And there is nothing in reinforcement learning that talks about identifying actionable dependencies or independencies. It's not that you can't do it, but that's not what it's designed.
Oh, big question. Okay, I'm working on a paper on causality and reinforcement learning, and partly inspired by these other questions. So I almost, if it had been further along, I would have asked to maybe give another talk. See what you guys
We'll
think.
invite you back.
I'll come back. Yes, I think that seems okay, but that's a whole. Okay, it's great ways, but yeah, great way to address credit assignment, causality, all these questions. Not really solved. Okay, so let me explain maybe why. Why reinforcement learning? It's actually very natural for sports. But terminology is different. So I talked to both sides. I'm just going to make a bit of a translation. So reinforcement learning, we talk about episodes. In sports, it's very common to divide the match into segments. For example, in hockey, we would have 3 periods. In RL, we talk about rewards. So in sports, we have some kind of notion of points, of goals, right? Something you're collecting along the way. The value function in reinforcement learning is what I've been calling the X value. Advantage. Prediction. So what's often called a prediction problem, for example, in Rich Sutton's book, is basically learning the X value function. So it's already been well studied. Right? In RL, we're often interested in control. So building an agent to actually act, and that we can't really do in sports analytics, right? I'd love, actually, it would be great. I'd love to be able to say, let's try, deploying Sidney Crosby on the right wing for a match or two. But not even his coach has the power to do that. Certainly not.
One of the nice things about the diagram Russ asked the question for is that level of explanation at the next level of detail is actionable for a coach, because when Russ said, oh, but what about the opposition, the adversarials?
Yeah,
that's information for a coach to avoid the adversarials, and that you can do.
Yes, that's a very good point. There's a whole, so everybody in sports analytics is always thinking about how can we get the teams to adopt our insights. So I can say more about that. But for now, I just want to say it's all offline learning evaluations, and that's partly why we have these issues with compounders too. Okay, so in RL we use Markov models. So I just wanted to describe how you can set up a Markov game model for the NHL. So we have a transition graph, we have agents, we have states, actions, transition probabilities, rewards. Markov game model has been around for a while. Littman, I think, wrote the first paper in '94, and So what's different is in a Markov game model, you have multiple agents, and so instead of looking at a single action at a time, you look at a tuple of actions. So the way we set this up, we're going to have two agents, a home team and an away team. You could do different levels, and that's partly why what I get back when I do representation learning. So a way to think of it is that we're pooling the data for the home team players, we're pooling the data for the away team players, and we're modeling average or random team players. Right, so what is the average impact of a shot over all home team actions? State space, well, we have context features. For example, we know the current goal differential, we know what period we're in, how much time remaining. Aha, and here I put continuous. We're asking about this. Time remaining, continuous. So there's like instantaneous features that you observe. We have a discrete set of actions, 13. These come from Sport Logique, but they're quite similar to what the NHL has. And then we have event data. So now I'll come back to this question about the continuous. Maybe I'll run with this. Okay, so just to visualize this, so we have these discrete actions that happen at discrete times. That's why I was saying this, and we know at a given time what player has the puck and what they're doing. Okay, and then you can think of them moving, their action is moving the puck to a new location. In event data, we don't know where the other players are. So I often say it's like listening to a match on the radio, right? You're just hearing, oh, Crosby's carrying the puck. Whereas if you watch it on TV, you see everyone. You can get event data from the NHL. So let me maybe show. Okay, so if you go to NHL.com and then you're interested in some particular game, this is Blues against Avalanche, you click play by play, and then it shows you, okay, that was a face-off at 20 minutes, and then right before that, there was a blocked shot, then before that was a shot on goal, and it tells you also the location, so see where the action took place, and it also tells you who performed the action, right? Yeah.
So they got that from analyzing the videos, or they have some sensors measuring that?
I believe this is all manual annotation. Yeah, yeah. So, SAP is sponsoring it. So, but, yeah, no, it would be. And then there's a whole thing, the whole little subfield, if you look at Sloan papers on how much bias is there in the annotations. But it is available if you don't want to bother pre-crawling. I posted a data set, I think, for 5 seasons where we crawled a lot. And okay, it's not the most recent 5 seasons, but if you just want to explore, try some RL methods, then I think it's convenient to get. And most of the experiments I'm reporting, we use a proprietary data set from Sport Logique. Tracking data seems to finally be becoming available. I don't know, I don't have it yet. Generally speaking, it hasn't been available for hockey.
Is the proprietary data proprietary because Sport Logique takes NHL published data and adds value to it by annotation, for example?
Yeah, they do their own annotations, basically.
So the
So
proprietariness is the added value of them analyzing the available data from the NHL.
yeah. So well, they actually analyze the videos directly, annotate and do computer vision. But like I mentioned, they have 13 action types. I think the NHL has only 10, so they go into more detail. Yeah, proprietary is kind of annoying. I mean, I get it, they live on that, right? But it's like hard to share, it's hard to make progress. The field.
It's like medical data.
Medical, oh my gosh. Wow. But Daniel Baumgarten has solved all this, right? It's the UFA. Okay, but then that's really digressing. Okay, if you prefer visualizing data as tables, so play-by-play data looks like this. Okay, so you got all these rows, they're ordered by timestamps, which I guess I didn't show, but okay, so every row is discrete. You see the action, you see where and where the action occurred. So that's our data. That's what they look like. we've got, just to give you more of an idea, for just one season, we have 30 teams. Got over 2,000 players, over 1,000 games, and over 3 million events. So it's a big data set. And so that's just one season. So potentially we can learn a lot about the game of hockey. It's really nice. And no privacy issues because the players are acting in public, right? They're on TV. So okay, so people try different ways to learn the success probability. So I'll do this maybe a bit quickly. So one choice you want to make is whether you want to discretize, especially the ring. So I showed you briefly with Eric Carlson discretization. And then if you're willing to move to discrete model, you can do dynamic programming. So I built a model like that for the NHL. Timothy Chan, who's a CRC at U of T I mentioned, and Marty Puterman have built a discrete Markov model for National Football League, American football. Puterman, some of you might know, as the author of one of the great classic textbooks in Markov decision processes. He's actually done Go too. Anyway, so he and I are really, we think alike, except he likes, he wants to do everything discrete. And, okay, so then if you don't want to discretize the continuous data, you can work with the raw data. You can do this with reinforcement learning, and that's so where I'm at. Now, most people in sports analytics instinctively fall into what I call the classifier approach. Okay, so they extract features from a continuous sequence, and then they say, okay, we want to predict whether or not we're going to score eventually. Okay, I have backup slides on this. Rich Sutton in his book calls this the Monte Carlo approach. So it's really Monte Carlo versus TD, temporal difference learning. And I've been on a crusade to get people in sports analytics to use temporal difference learning. It's an uphill battle, so I can tell you more about how that has gone. But that's what they fall into. There's a group in Leuven who has, for soccer, have developed this classifier approach. Won a Best Paper Award at KDD 2019. It's a good paper, so it's possible. But yeah, so we stay within the RL. So we use an RNN to process the event sequences. We divide the match into episodes according to possession. So when a team loses the puck, that's when their possession ends and the reward is basically 0. So that means we have a sparse reward situation where most of the time the rewards are 0. We use temporal difference learning. Okay, I have a backup slide on that. I'm not saying it's an obvious idea. In fact, I think it's a brilliant idea, temporal difference learning. But basically, you're making your estimates at different times consistent. Successive estimates consistent, and you can also think about making consistency not just with the next estimate, maybe the next 2 estimates, the next 3 estimates. So there's this hyperparameter lambda. There's only one work I know that's actually tuned lambda. This is Dick and Uwe Brefeld for soccer, and I'm highlighting that as a technical detail. Because next time I try to learn a value function, I want to do that too. I want to tune the lambda. So I recommend doing that. And I would love to know what the optimal lambdas are for different sports.
I would like to believe that there are such, but I don't think there are.
You can read this paper. I can say a bit more about that because it's kind of measuring how quickly does the impact of an action dissipate. Right, so how far
for professional soccer and for high school soccer and for
right. You can do So I think it's like one number that would be really interesting to know.
Well, I think you can use it to calibrate across the situations of assessment. I would be surprised that there is a scientific basis for picking 0.71 as Bundesliga as opposed to 0.64 for North American New Jersey soccer, for example. That's what I'm skeptical of.
Yeah, probably connected to calibration. Okay. Oh shoot, I may have to. All right, I'm gonna skip. I go a bit faster. How do we know that this works? Well, we don't have ground truths for player ranking. We can do some qualitative inspection. So, for example, here's the function that DeepRL learns for a shot by the home team, heat map for the probabilities associated with different locations. And it makes sense, right? So you have closer you are to the goal, the more likely you are to score the next goal. Being straight is better than being at an angle. If you're really far away, you have very low chance of scoring, which is actually interesting because there's no data there, right? Players don't try it, so the system is actually generalizing.
I like the behind goal.
Was that?
I like the behind the net as well. It's worth it.
Oh, yeah. So we're unlikely to score if you take a shot. So yeah, good point. We have comparison. Okay, so there's all kinds of player ranking metrics out there. I mentioned plus minus, so we compare with that. Okay, so one of the things we do, like I said, there's no ground truth. And one of the things we do is we look at standard stats that are published by the NHL and other sites. And we say, okay, what we want is we want a high correlation because they wouldn't publish these stats if they weren't important, but not perfect because after all, we think we're adding some information. And so if you go with that approach, then our GIM method, has most of the time the highest correlation. The three bottom ones are all RL methods anyway. It's also consistent through time. Yeah, let's push that. Okay, so the last topic I want to go into a bit of detail on is learning player representations. It's another reference. And so the question is really, how are players alike? How are they different? And the way that we want to use X-value learning to measure that is to say, well, what's the differential impact of having one player rather than another? So here I give, like the intuition is a shot by Schulte is different from a shot by another player, or shot by Messi is different from an average player. And we can measure that. We can say, well, what if we add the identity of the player acting to the context? So what I've shown you so far, there's nothing about specific players, it's all just random players. But we can change that. And so we can add Schulte's ID, but we don't want to add his ID, we want to add an embedding. And so, and moreover, we want a dynamic embedding because, to characterize Schulte's strengths and weaknesses, they may well depend on the match context. Okay, and so then, we use a variational autoencoder, a dynamic variational autoencoder model from the Myla group. And so the main idea here is to train the variational autoencoder to solve the player identification problem. Okay, what's the player identification problem? Player identification problem is you've been watching the match and you're seeing a player, imagine you're seeing them on the screen, and you're asking, well, who is that? Is that Schulte? Is that player number 19, player number 17? So this is a real problem that people work on computer vision, right, to track players. And so when we train the variational autoencoder, we use an elbow. And okay, and if you've seen this before, then this will be obvious. If you haven't seen this before, it will be impenetrable. Okay? So let me just highlight the main things. So in the training objective, first of all, you say, okay, given my player embedding, how well can I predict which player is playing? Okay, so how well am I solving the identification problem? And then you have this term where you say, okay, here is my method for embedding player I, right? So this is mapping, say, Schulte to the embedding for Schulte. And how different is that embedding for compared to the embedding of an average player? So this gives you what's called a shrinkage effect. Okay, so the KLD term is encouraging you to use similar embeddings unless you have evidence to the contrary. Okay, and then I'll just mention this. This actually translates into a Bayesian hierarchical model, which is what Bayesian sports statisticians use to model individual players, where you have a common prior over all players, and that common prior is like regularizing your model for each player. Okay, so it's actually a very beautiful connection, and the fact that it just falls out of the elbow, it's really nice. Might go into that. Okay, and then you can visualize, and the visualizations look pretty good. But let me say another way to evaluate is on downstream tasks. So here what we do is we take our player embedding, we say, suppose we know that this player is playing and they're taking a shot, and are they going to score a goal or not? Okay, and then you see the top three methods are ours, and you see pretty good. F1 score, not exactly overwhelming, but still the best. Yes, making substantive improvement. You can be more ambitious, and you can say, okay, I want to predict the final match outcome, and I'm going to add my player representation to help do that. And here actually we get really a nice boost. So this is a very hard problem. Mean absolute error goes down substantively, and all these three methods are actually all variations of our approach. So it does seem to be learning something useful. Okay. All right, and I will just mention these. So we've tried different parts of RL. So I'll drop these keywords in case you're, this is your area of RL and you want to know more. We've done an inverse reinforcement learning, so where we try to learn what are actually the objectives that a team is pursuing. Okay, and there's been follow-up work on that in soccer. We've done distributional RL. This is our latest last year at NeurIPS, and this is probably one of the directions that I'm most excited about. So really fundamental question that comes up in sports a lot is risk versus reward. I give an example in basketball. You can take a far shot and win 3 points if you succeed, or you can play it safe and take a close shot, you get only 2 points. Right? And so you have that trade-off, and you can model that by saying, well, how about we don't just look at the expected value, we look at the variance of your success. And a very common theme by sports analysts is that they criticize coaches for being too risk averse. Okay, so this is kind of many blog posts, many articles. And with distributional RL, where we model the whole value success probability distribution, we can actually capture the range of outcomes. So here's a value ticker where you see a band of uncertainty. Okay, and then we can use that to measure, for example, risk aversion and include that in our player metric. So that's exciting. Yeah, then evaluating lines formation. So this goes back to some of the issues we were discussing. What's the right level? There's some preliminary work by a Swedish group where they looked at pairs of players. The holy grail is basically the offline RL problem, which is, can we tell a coach, here's the right thing to do, without being able to experiment. Jenna Ween's group at Michigan, I think, has an interesting paper looking at a specific issue of basketball where they tried to do that. Okay, utilizing tracking data. All right, so let me summarize so we have some time for discussion. So I think learning expected values is the fundamental task for sports analytics. That's what we need to do. And it gives you a new powerful approach to assigning values to actions and to ranking players. I think reinforcement learning is the way to do value function learning. And we got many tools. I'm showing you, right? Inverse RL, temporal difference learning, distributional RL, that we can apply in sports analytics. I think that we should really use methods that can natively deal with continuous locations. Timothy Chan and Marty Peterman tend to disagree with me on that, but okay. But we can do it, okay, using neural nets. And then a couple of current directions I wanted to emphasize are, what I call precision sports analytics, where we make the model specific to teams and players, and the risk rewards trade-off. Last thing is I wanted to plug a sports analytics group. There's faculty members from 4 different faculties in it, and we've been running seminars online for years now on many different sports, many different topics. So if there's a topic in sports you're wondering about, I think we have a talk on it. And if not, let me know and I will get them to organize one. All right, so thank you.
However, I want to ask a very general question,
Okay,
because the trajectory I learned about working with the Oilers analytics group is it gets back to actionable things.
Mhm.
And none of the discussions were ever independent of the opposition. So if you like, there's an element of game theory.
Yeah.
What will you change, or what will change to scale the approximation of the X value functions when you're considering all possible interactions with all players, which is the worst case? But the NHL publishes
Mhm.
who is on the ice at what time all the time, so you can tell.
right,
So could you build the same kind of X value approximating for a game? The configurations of the players, so that a coach can say, this is the playoffs, utility is high. I want this person always playing against Sidney Crosby, for example.
okay, so.
So what would you change in the method, just vaguely?
Right. Okay, so I think there's a couple of issues. I just want to say one thing, a piece of advice I got from a sports analyst who was working for the Whitecaps.
Yep.
And he said, it's much easier to sell information that criticizes the opposing team than to sell information that criticizes the team you're advising.
So characterization of the opposition.
So the opponent modeling is easier to sell.
Yeah.
So, okay, so that I think is a good, I've kept that in mind. Now I think you're asking something a bit different. Yeah, I think maybe you're asking something like, could I recommend, well, you're playing, you know, tomorrow night you're playing the Penguins and now you should be fielding the following lines.
Right.
Yeah. Okay, so my colleague Tim Schwartz has written a paper on doing that for cricket. So finding an optimal lineup.
Yeah.
It's also related to fantasy play. I don't know if anyone's in a hockey pool here, where you're also trying to find optimal lineup.
Yeah.
Actually, I gave an invited talk at a sports optimization workshop on the constraint programming conference this August. And everyone there was doing combinatorial optimization to figure out optimal teams for fantasy play. And I said, yeah, if you have this, you could also, I think it would be 1-1 really. You could do optimal combinatorial optimization to figure out the optimal lineup to deploy against players, against the other team.
And the reason for asking is back to Russ's question about the Eric Carlson.
Yeah.
At the next level of detail.
Mm.
Every hockey coach I know knows how to use that information and says, make sure that Carlson is not playing against a hard checking right winger.
Yeah,
Because
yeah.
he moves the puck in that way.
Right. So they do it informally.
Yeah.
And so I can send you my slides if you want from the workshop, but one of the things I was saying, what we can do with computers, we can try all these different possibilities, right? Like a coach is going to consider maybe 3 to 5 permutations, right? We can consider 10,000. And we just need one win, right? I mean, maybe, you know, if we take our top 10, like 9 of them will be nonsense, right? But if there's one where the coach is like, oh, I hadn't thought of deploying my players in this way, that's interesting, then that's a win, right?
Well, it's worth trying. Maybe there's a reason you didn't think about it. Maybe it's a bad idea.
Yeah, so I think 9 out of 10 will probably be nonsense, right?
Well, the whole,
Or they'll be missing something that he knows that we don't know.
the whole scope of possible multiple rankings from X values is you're managing hypotheses a coach can experiment with to try to.
Yeah. So I think like I said, I'll send you my slide. I was trying to get these guys at the constraint program. They're all into combinatorial optimization. I was saying, well, maybe you can help me here. I have the X values, but to really make it actionable, I need like optimization, right? The place, like I said, where they're really willing to do it is fantasy play, because then they get into the betting and the winning, and they were like, it's amazing how much effort these professors were willing to put into.
Maybe it all comes back to betting.
Yeah, we're humans, yeah.
So one of your the player ranking metric that you mentioned was like GIM, right?
Yeah.
Like, could you say a little bit more about it? You said it was like a sum of the Q values, like summed over all actions for a particular player.
Yeah, they're let me see where I find it. It's the impact values, which are, if you're thinking RL, their impact is like advantage. I don't find that advantage. I don't know if you know what the advantage concept, but anyway, it's the difference, right, between the Yeah, I didn't write in Q. It's the difference between the Q and the V.
Right,
So where was I? Yeah, and then we add that up.
so add that up over.
All the actions. So if Jason Spezza, let's say he performs 1,000 actions, then every one of those actions has an impact.
Right.
And we add up the 1,000. You know, we'll be adding up 1,000 numbers.
So it's conditioned on the player representation and marginalized over all scenarios.
Is overall scenarios. Now this one is not. This is before we did the player representation.
Okay.
In the NeurIPS paper, then it's conditioned on the representation. Yeah.
So then, what is it conditioned on here? Like how is
This,
it?
just that, well, the context or the state. Are you like in RL? Are you
Yeah,
comfortable? Okay, well then it's conditioned on the state,
Okay.
which includes the history.
Right, for this particular player ID, because it's just an ID here, right, as opposed to a representation.
Yeah, so, okay, so let's say he takes a shot and we just say, okay, how much is that shot worth for a random player? Just in general, right? If you're close, okay, so like, if you're close, let me maybe give this picture here. Here, right? Let's say he takes one shot from here and one shot from here, right? So now we get two numbers, which have really nothing to do with him. Those numbers are how much is a shot worth in general from this location, and then we add up those two numbers.
Okay,
But once we have the player representations, which I only got in 2020, then we can add that in. That gets more interesting. Yeah, that's something to explore in more depth. Yeah.
I kind of have two questions that are kind of related.
Great.
How do they measure short-term impact? So I guess this would be more on the lines of like betting or like game prediction. So let's say like Connor McDavid got injured recently. So his history is amazing, but his very recent thing is going to have a massive impact going forward that isn't necessarily represented in his statistics. So I'm guessing betting odds, do they take that into account? And then also my other question was kind of just more theoretical, based around morale. Because I think at least commonly there's this idea, at least I'm a hockey fan and my families are hockey fans. There's this idea that like a lot of things people say like, oh, when a team is losing and then like a big guy, they get this big fight, that's like a rallying cry and then they're gonna go and win the hockey game. And I'm curious if that's true. Like, does morale actually have like a measurable impact on the, like in the most recent Vancouver game where they got scored on like immediately and they scored on themselves and then they just tanked. And it was like, did that actually matter? Was that important in the winning and losing of this game? Has anyone done kind of the measure? I don't know how you could measure that, but I'm curious.
You want to answer?
No, I just think how much momentum that.
Yeah, that should be the idea of.
Oh, okay,
momentum
okay.
too,
Oh,
yeah.
wow. Let me say, unpack that a little bit. Okay, so the injury, so like I said, I'm doing an average value, right? So, and I don't actually know which players I injured. But I think maybe what you're looking for is, so for Sport Logique, I built a betting system. No, not betting, sorry, win probability system. So we don't actually put bets. And there we totally had all this stuff about who's injured, who's playing. We had to, it's like when we get the roster, you get the roster 5 minutes before the game, sometimes a minute into the game. And then we would update our predictions in real time because we had like extensive player models. So,
You could answer that question to start by having to capture events that are treated as potential change of momentum.
right.
The NHL doesn't do that.
Right. So, yes, so it wouldn't be hard to include, especially when we have the player representation, right?
Yeah.
The other question was, okay, what about when the Canucks score on themselves? So in principle, the X value function can tell you that, right? You should see, so if you think about, the value ticker here, right? We should see something like, oh, if you're early in the match and you score on yourself, you should see like a big drop.
But
So,
does that then take into the whole game? Like I just.
yeah, because now that becomes part of the context, right? And remember, our context is always the whole history.
Yeah.
So in principle, let me say in principle, this value function approach can totally learn that.
I didn't see an account for fighting. I know you looked at like shots and hits.
Yeah, we have hits. So,
Yeah.
yeah, so that's another thing, right? So if you have the data in that, it could also learn, certainly it can learn for hits, right? It can learn, oh, if you make a hit, I don't know, at a crucial moment in a game, that will have a big impact. Yeah, and momentum, by the way, in general, like across games, there's a small literature on that. There's a Professor at Cornell who's written on this, and they seem to claim there is no momentum effect. So it doesn't, according to them, statistically,
There's no such thing as a curveball.
statistically, if you lost the last 3 games, it doesn't make a difference. I don't know. But hey, if you could run our RL system, you know, and maybe we will find something then.
Yeah,
The first approximation to answer this question is that there is data that's relevant. Penalties are recorded. And you could look at that distribution to say whether there's certain preponderance of penalties at a time changes game outcomes and measure just statistically whether it has an impact or not.
There's also true player, the ice.
but you can tell the players get, at least in the NHL, like they get heated, like the coach took a penalty on, what was it, Monday? Like that has to have an effect on the players.
Yeah, I know the
Like, it's
intuition
just
of
that, like, you know, when players get thrown out, not that happens often,
Yeah,
but like that impact on the rest of the team's
right.
set, like, I don't know.
I think the deeper issue maybe is there. So we just model within the game, right?
Yes.
And we have episodes, position episodes. So if you could, in principle, extend, like make a sort of hierarchical RNN, right? Where you're at a higher level state between games.
Yeah.
Right, and then you start the new game in this global state.
Yeah.
And then you have local states. Yeah, we played around with that.
Well, the current approximation to the X values doesn't consider whether there are 1 or N players on the ice, right?
Yep,
It's just the aggregate data.
Yeah, and that can take into account too, like the coach's speech between periods, like when.
Right.
what-
Can I just ask, do you guys take questions from the chat, or is that's not usually done? I don't see any, but
I have my hand up. I don't know if you guys can hear me. Can you? Yeah.
Yes.
Okay. Hey Oliver, thanks for the talk. If you go back to the slide with the rank, with the like blue to red gradient, what exactly? Yeah, it's the one with the hockey rank.
You can't.
oh, the rink. I thought you said rank.
Not in soccer.
Did I? No, I think it's.
Yeah. Yeah, right there.
Okay, yeah.
What exactly is the gradient label here? Like, because it says X values after shot, but it goes from 0.55 to 0.8. So could you talk a bit about what the color indicates here?
Yeah, it's actually.
I thought X values was like a probability from the probability distribution, like probability that it impacts your team's success.
Yeah, so yeah, I went over that a little quickly. I look at the probability of scoring the next goal. Which team scores the next goal? So, and okay, like for example, if you take a shot, you might score immediately, but you might get a rebound, right?
Yeah.
And then that would be still considered part of the success. So, or
Okay,
another way,
so
the
is this
default is kind of 0.5, right? You say, oh, both teams are kind of equally likely to score the next goal. So that's why, for example, it's like if you just ask what's the baseline rate of scoring a goal from a shot, it would be very low, right? Because most shots don't succeed. So I don't know if that's okay,
yeah,
anyway,
like in terms of expected goals, like the highest expected goals is roughly like 40%. And so here I'm just trying to understand. So it's the probability, like long-term probability, like roping in whatever happens after, say, a failed shot or like a shot that doesn't go in. I just don't really understand why the scale goes from 0.55 to 0.8 here.
yeah, it's maybe not. maybe it's a bit more difficult. I guess it's more difficult to interpret than immediate goal scoring, but so if the teams are equal, right, then it's then this will be 50%, right? Each team has the
But you
same.
have the puck.
What?
Two teams are equal, but we have the puck. Is that-
We have the puck, exactly. So that's why we tend to be, I mean, we tend to be, okay, in all these areas, right, we're gonna be above even above 0.65, right? We have the puck and we're making a shot, we're taking a shot. So first of all, we have a good chance of scoring on the shot, but we also have a good chance of getting a rebound or continuing the attack.
So yeah, but this even like persists all the way to like your own blue line, essentially. Like it looks like it's still roughly 0.6, 0.65.
Yeah, here, right? So yeah, so if you, so now it's, I don't know how much data we have. That's actually a good question on this, but it's what it's saying, and it might be wrong, but what it's saying is that if you were to take, oh wait, I gotta go. If you were to take a shot from here, the chance that let's say that your attack will succeed, maybe not immediately, but that it will succeed is, yeah, something like 0.65.
Like behind your own goal, should, you know.
Right, and I think the crease is darker probably because they actually have more cases of like goalie goals than they do of like anywhere else in that area. So that's what's accounting for probably like the crease being darker than everything around.
Probably
That's
just
lower
being
muscle.
colored. Probably not the
Yeah.
heat map,
Oh, yeah.
which is like.
So
colored.
here,
It's interesting.
so we don't have, I mean, yeah,
Right, very
you get
good.
into interesting issues about, you know, which come up in RL a lot is with like the low frequency states, right?
Yeah.
But yeah, and I think it's like, because what Russ was saying, first of all, we're in possession, right? So our chance of scoring the next goal would already be higher than 0.5. And then if you're taking a shot, generally speaking, you're doing that because the player thinks they're in a promising position. So I don't know, it sort of makes sense to me. That would be fairly high. Yeah.
I want to thank Oliver, and then if you have more questions, you can ask him, then I just want to finish. So
Okay.
thanks for.
Thanks.
Doesn't make sense, so. And also I do worry about this a lot, and we try to make these interpretable by extracting rules. So then I extract rules and then I look at the rules and say, do they really make sense or not? So,
That's where interaction with the subject matter expert, like coaches.
Yeah,
makes a
yeah.
real difference.
I do always worry about whether this thing is buggy or not. So I don't want to brush that off. But that's also why we look at calibration, right? It's reassuring to me. Right?